Okay, let's continue. So till now we have just discussed some basics, how color is formed and perceived. And now let's get to the actual rendering process. So we got this equation to determine the color for a given point of the object in the rendering. It looks complicated, right? So does anyone know this equation, or can anyone explain, or should I? So any clues what's going on here? Yeah?
Does it have anything to do with Lambert? The L?
No, L I think in this case stands for light. I'm not sure what else, like why do they use L in this case, not other letter, but Lambertian reflection is just one example. Yeah, but not for all cases. Yeah?
I'm not sure, but is it W is maybe the illuminator, and the other one, no, the W with the dash thing is the light source in a way, with the luminosity, and the W maybe be the observer, and the X might be what the object reflects, but I'm not sure. I'm just guessing.
You're, somewhat close. Just make sure that we're, streaming, because no streaming gets stuck from time to time, and I'll just check the program. Yeah. So the one on the left is the light output. So L, I assume stands for light. So light, that is output, those are the final one, the result. And we have 4 parameters here. We have X, that is the location in the space. So it's just like for simplicity's sake, but it's actually X, Y, Z coordinates. But like just overall location is signified by X. Omega is the outgoing direction and outgoing angle, or like the angle we're observing, that X point. We have delta. Any guess what it stands for? Or it's it's lambda, right?
Yeah, it's
lambda. Sorry, yeah. Any guess what it stands for? So when we talked about reflections and absorbing some amount of light and some of them not, and reflecting just red and not green, that kind of stuff. So what is important to have here? The wavelength. So lambda is wavelength because, for example, from this point we can have absorption for red wavelengths and reflection for green wavelength. So it's important to have the wavelength. This is just time, so like for a given time point. So if we change this one, then the stuff might change there. So we have location, observation angle, wavelength, and time. So what's happening on the other side? Any guess for this one? So if LO is L output, what can LE be? And I can say that it's used for very particular cases, and we usually set that to 0. So that is emission. So if something is emitted directly from this point, so usually we just work with reflecting surfaces, so some amount of light came from the source and it's reflected. But if this itself is emitting the light, then it should be also considered here for the same location, direction, wavelength, and time. So this parameter is usually equal to 0, but when it is not, it's usually used to render light sources, for example bulbs or displays. For example, if I wanted to render this scene, this room, I would not set that to 0 for example, those illuminations, because it's, except for reflecting sunlight, it's also emitting something itself. Okay, and then the reflection part. So we integrated all over this hemisphere, and for all directions we have like those parameters. The first parameter is a reflectance function, so BRDF, and we will see what BRDF is. It's bidirectional reflectance distribution function that simply shows what portion of the energy is reflected from a given point. Like we have, again, the same location. In this case, we have incident angle, so the angle the illumination beam comes. So we have reflection angle, to which direction this one goes. We have wavelengths and time. So what does the function return is that how much energy for a given wavelength at a given time point is reflected to which direction. So when this angle changes, then when this angle changes, the result can change, or like when we change the reflection angle, we can have different number, because like it depends on which direction the light is coming from and which direction it is reflected. So the Lambertian surface that is mentioned is the one that reflects equal amount in all directions perfectly. But in reality it strongly depends, because we have more reflection in some direction and less reflection in other directions. So this one shows how much of the light is reflected in a given direction for the light incident from a given direction. Yeah. And yeah, this is the incoming light, amount of incoming light itself for, again, the location, incident angle, wavelengths, and time. And the last one is incident angle attenuation. So when we when we decrease the incidence angle, the light is spread to more area, so its intensity or brightness decreases, because the energy is shared, is spread on larger area. And sometimes this parameter, weakening parameter, is also given by cosine theta, simply just the angle. And n in this case is surface normal. So yeah, if we have a look here, what I mean is that if it's coming from the 90 degrees, we have all the energy fixed on this surface area, while if it's 45 degrees, we have some given energy that it has to be spread on this area, and if it's less like lower angle, it's spread even larger area. So we have like a small amount of energy for this point if light is coming from that direction or from this direction. That's why we need this weakening factor to include. But how do you find this equation in general? It's pretty complicated, even though it's easy to understand because we don't have many variables. So again, like to just go through that to make sure everyone understands. We have output light for a given point in a given direction for a given wavelength and at a given point of time. That is a combination of emission plus the amount of light that is reflected to this direction from the incident light, and also we have a factor to control the weakening factor due to the angle. But this is the ideal case, like this is the ideal case, theoretical one, where like everything is under control. However, it's extremely costly in terms of computation to calculate this equation for all points, all angles, all dimensions. Therefore, we need some simplification. But before that, just go through some terms and processes that's happening there. Like BRDF, as I mentioned, is a bidirectional reflectance distribution function that describes light, how the light is reflected and in which angles. And it has one very significant limitation. So any ideas what can't be described with this one? Why is it very limited to very particular cases? Yeah.
Glass and mirrors, maybe, since it says it works only for opaque surfaces.
Yeah, glass is a good example. Yeah, because it's translucent. Yeah. So this one only describes the surface reflectance. So when the light interacts only with the surface. But with this function, we can't quantify the amount of light that it penetrates the matter that is transmitted. So we can't really work with translucent objects with this one. Actually, except for the reflection that is very well characterized by BRDF, and usually opaque surfaces can be well described by BRDF, but we have problems when we have light penetration into the matter. That you have other factors coming, like except for the reflection, there is absorption. Some amount of light is absorbed, and most interestingly, we have refraction when the light is bent, so it changes the direction, and we have the transmission when the light from one side of the object goes to the other side of the object. And for rendering translucent materials, I'm working on that right now. I'm using Mitsuba renderer in the tools. It's simplified to like some parameters. For example, just as an example, I'm using absorption, scattering, and phase function. So absorption is the probability that the photon of a given wavelength is absorbed. Scattering, it's just like probability that it changes the direction after the bounce. And phase function defines what is a probability to the photon to go to a particular direction after the scattering, after the bounce. So to make it simple, I use the isotropic phase function that says that it's equally probable that after the bounce, the scattered photon goes to any direction. But this is the things that we need to kind of control and think of when we're working with translucent materials, because when the light enters the object, there are like absorption and scattering happening, and we want to quantify that. And refraction in this case, it's very simple. It's just like the light after entering the edge of the two different media is bent and changes the direction. And yeah, here is just example of translucent material where this subsurface scattering happens. But yeah, there are like lots of objects and materials in real life that are translucent as glass, as you have mentioned. Human skin is translucent, and it makes it extremely difficult to be rendered realistically. And yeah, we have many different candle is translucent, and liquids, lots of food stuff are translucent, and it makes it difficult to render realistically. Yeah, so the comparison, we had BRDF, bidirectional reflectance distribution function, that shows how the light is reflected on the surface. But for these ones, we need the bidirectional subsurface scattering function, distribution function, which, except for the surface interaction, shows how the light interact with the matter in depth. So when the light enters it, what happens, whether it's absorbed here, or whether it's scattered in this direction, or whether it's transmitted to the other side, or whether it's back reflected. So this function is more complicated, and we need more variables to describe translucency. Yeah, till now, so far it's clear, I hope. But one very important question: why this can be problematic for gaming and what you should consider. Yeah.
Well, you kind of want things to look realistic if you're making a photorealistic game, but if these functions are very kind of computation heavy, like it's kind of a struggle to get them to go 30 or 60 frames a second, 60 times a second. Doing that for all possible points is hard, computationally.
Yeah, absolutely. So it's computationally very costly to calculate and solve this equation for every point in the scene, and it makes it almost impossible to be real time that is needed in gaming. For example, I'm rendering now some images for my studies, and I want them to be as physically accurate as possible, and rendering of a single image takes up to a day. So it's for a gaming you need something really fast. So we need to, instead of solving this equation with very good precision, we can simply approximate it. Yeah, some techniques to approximate. I hope those stuff already sound more familiar to you than the previous slides. So anyone who could briefly summarize what is ray tracing, photon mapping, if you have any experience with them? Yeah.
Well, ray tracing for sure is like you simulate each similar light ray and read the value that was when it's like you have say 3 bounces, and then you do 3 bounces and take sample the pixel value of that particular pixel and then put that on the screen, sort of. So you fire a ray for each pixel from the image. And it bounces, right?
Yeah.
Or from the light to the camera, but it depends.
No, it's the other way around. Yeah, you start from the observer.
From the camera.
From the camera.
Yeah. But the way you simulate each light ray, as least as many as you can computationally do realistically.
Yeah, so you fire a ray from the observer into the scene, and it hits some solid body, and by firing these rays you find the closest possible intersection, and then you find the luminance values for that point. So from where you start from the observer, you hit the surface, and then you see what is the illumination to that point and calculate it that way. It's very counterintuitive. Like usually in real life we have photons emitted from the light source, they hit the object and they go to the observer. But why do we start from the observer, from the camera or eye? Yeah.
Less samples to less calculations, because you know what you're gonna see, so you don't have to do anything that's outside of your view.
Yeah, exactly. Yeah, that's absolutely true. So when you start from the light source, the light goes to like many different points, but not all of them go to the observer. So you just focus to whatever actually goes to the observer. But this one has one very significant shortcoming. It's that it's very bad at rendering soft shadows and caustics. So when you start from the eye, you go to the point, you find the light source and you calculate that area, but you can't really model caustics that is a result of refractions, and also like soft smooth shadows that result from the several bounces and indirect illumination. And it's pretty slow. Photon mapping is the other way around, as we have said. Would you like to say? So for photon mapping, it's like 2-level process. On the first level, we start from the emitter, from the light source. We bounce photons toward the object. And in this case, yeah, another downside here is that we don't have control of the material properties explicitly. Why here we have explicit control of material properties, because what happens is that we use Russian roulette, so probabilistic approach. For example, we know that material properties for a given point say that it's 90% probable that it's reflected and 10% probable that is absorbed. So if we have, for example, just make sure that the camera is. Yeah, so for example, if we have, for a given point, this kind of spectral reflectance, like very low reflectance in blue and then too much in red. And the photon that is in this wavelength is coming. So we have a very high probability that is reflected and low probability that is absorbed, and the other way around. So in this one, we apply probabilistic approach. I will just move just make sure that this is visible. Yeah, and the camera. So we run a Russian roulette, considering our probabilities, get a random result, whether it's absorbed or reflected or scattered to other direction. And then we have another bounce. So this photon goes to other direction and the other direction until we terminate the process either by absorption or by manually setting the limit of bounces. And after that, we have the maps. So of all points, usually there are two maps: the global map, where like first the first hit was done, and also caustics maps, where all the caustics, the results after reflections of indirect touch come. And we store the locations of the photons that for the point where they hit the matter. And on the second level, we use just ray tracing. So we start from the observer again, but instead of calculating and solving the equation for that point, we already have the photon map. So we know where the photon landed, and considering the neighboring photons, we calculate the value for this point. And for introduction of the caustics, we can simply use caustics map. So on the first stage, we fired photons. They hit the matter at some point. We stored these locations, directions, everything. And on the second level, we started from the observer, came up to some point, and we have a photon map. So we know what are the photons, how many photons do we have around this. So we calculate the lighting intensity for that point in that way. But this is also pretty demanding in terms of computation, but it can realistically render soft shadows and caustics and all the effects that result from the indirect light source. So when we have light coming from several bounces. And why caustics are so important? Like this is some renderings from my study. So those ones are physical, real images. So this is a photo, and those ones are renderings. As you see, caustics can be a very good cue for translucency perception. So when I asked people to rank those spheres by translucency, they used caustics a lot. They looked at, so the caustics are these bright areas in the shadows that result from refraction. And as you see, like for translucent materials, we have bright caustics. For like this one, we have very dim one. This means that it transmits little light. And for opaque ones, we have completely dark, hard shadows. And this study is a different one here. The material of those spheres is identical. It's the same material. But we wanted to remove these caustics and secondary, the light that is result of these secondary bounces in a physically accurate way. So what we did is that we put the black floor that absorbs everything and doesn't reflect the light back. So when the light comes from the illumination, some of them is reflected, some of it is absorbed, but some of the light goes through the object, and then we have the caustics, and then it's reflected back. So it makes this sphere look even brighter. And the experiments have shown that when we remove this back reflection factor and this caustics from the scene, people perceive the object less translucent, even though the material properties are identical. Like this one is seen as more translucent because we have more light bouncing back. And also it's important for realism perception because this one is cropped and put on the black floor, and many people say it's not photorealistic and it's not realistic. Something's wrong with the physics here because we should have these caustics here, but considering the overall brightness of this one, but it's missing from here. And on the other hand, the scene was rendered using the opaque sphere, so there was physically accurate shadow, like dark shadow. Then I cropped this sphere that is translucent into this scene, and people also start saying that something's wrong with this one because we have the translucent sphere, so they expect having some caustics here. So what I want to say with this slide is that sometimes it might remain unnoticed, that also happens, but in some cases having accurate caustics can be very significant for photorealism. Yeah, so considering the slides I've discussed so far, can you guess which of the scenes is rendered by ray tracing and which of them by photon mapping? Yeah?
One on the left is rendered by ray tracing, one on the right by photon.
Yeah, what are the cues that tell you that?
The right one has caustics and soft shadows, and the left one doesn't.
Yeah, and anything else? So we have this color bleeding from the walls. You see reddish and bluish tint here, and we definitely have considered several bounces and larger path of the photon because it's back reflected to the ceiling. We have lighter walls because directly no light falls to here and here, but due to sorry, I thought you saw my mouse. Yeah, so directly no light hits the ceiling or the walls, very little of it, but considering this indirect light, so reflecting it from the sphere and hitting the wall, so all the path that we have in case of photon mapping, we get this kind of more lighter environment, while here we don't have that, so we don't consider from the observer's point of view that we have indirect light and we can have any luminance for the ceiling, for example. But yeah, shadows and caustics are very good cues as well. So other models, path tracing, that is very popular these days. To make a long story short, it's similar to ray tracing, but it's kind of brute force version of ray tracing. Instead of firing single ray from the observer, we consider lots of different rays in many directions, and instead of calculating just like value considering a given illumination, for this point we introduce this Monte Carlo probability Russian roulette thing, so we can, and we calculate several different we calculate the value considering the probabilities of this material, and then we simply interpolate values for different rays. Yeah, you can see here, if you just fire 10 rays per each pixel, you have like some noise because it's probabilistic approach, and you just get random cases But when you increase the number of the rays shot, you interpolate between larger number of rays shot towards this pixel. So in ray tracing, we just shoot one ray to this one and calculate for that case. But in this case, we have lots of rays coming to this pixel. We consider probabilities due to surface properties, and then we get values for each ray and we interpolate them. And higher the number of rays, higher the quality, but it also increases computation time. Yeah.
Does this have any benefits over photon tracking, photon tracing?
You mean?
Does path tracing have any benefits? Why would I use it instead of photon tracing?
It's a good question. I think because it can lead to, because in photon mapping we still approximate, like we have just map of the photons and we just calculate a value for a given pixel that has not hit at all considering those values, while for path tracing we start from the observer and we make sure that we hit with our rays all the pixels in the scene. But on the other hand, it's very, very demanding in terms of computation. I'm not sure exactly because it can depend on the applications, but the first thing that comes to my mind is that we make sure that all our rays shot from the observer hit the pixel. But that's not the case in photon mapping. In photon mapping, we have the map and we kind of calculate considering that values. Any input from anyone who has experience with this? Yeah?
I think it's also more physically accurate to use path tracing. Like at least you would use it for if you want really hyper-realistic images. Because photon mapping is still an approximation.
Yeah, that's what I was saying. Yeah, it's approximation, yeah. And in this case, you actually find it for each particular pixel. But yeah, if I should continue this topic on the next lecture because we have lots of things to go through. So I will kind of make research of pros and cons and summarize them and bring it next time if you want. The radiosity is pretty old technique. It has its roots in 1950s, and it splits the area into patches of different luminances, and it approximates just diffuse reflection. So it assumes that we have diffuse reflection in all points, and the intensity is observer independent. So regardless the angle we are looking at it, we have the same intensity. It's very primitive, and then it kind of approximates across these patches. So we have example here, like the left one is just example if we had simply direct illumination, and this one considers just diffuse reflection and also kind of interpolates between different areas, and we have this kind of smooth transition. But in general, it does not support specularities. It assumes that all of the surfaces are diffuse reflecting, and that's very limited one. And scanline rendering, it's not rendering technique in itself, but it's a technique to decrease the amount of information and the areas we want to render. So it's used in combination with other rendering models, but the key thing here is that we simply identify which points we need to render and which do not. So for a fixed Z value for a given like two-dimensional plane, instead of working with pixels or vertices and edges and triangles and polygons and all those stuff, it simply scans it line-wise, starts from top Y and scans whether we have a point here, and then identifies what is first, what is occluded, what is second. So it gives us information what should be rendered, whatever is in front and what is in back. So should be just thrown away. For example, for this one, when we scan this line, it says that okay, the z, considering the z value of this xy coordinate here, this is the gray one is in front, the dark gray one is black, so you won't see the dark gray one because it's occluded. So just throw it away and just render this point that comes from this one. So that decreases the amount of data and the amount of pixels that need to be rendered. And it's very fast. And except for, but even if we ran scanline rendering before rendering our scene, it still might not be enough to have the real-time rendering like in gaming. So for this one, in gaming, there are lots of simplifications that are used that make the process very fast. And we have the simple models. For example, let's start with, the light source. The real light sources are very difficult. They're very complicated. So they give like different amounts of light in different directions, and they differ. Like this, for example, this bulb or this illuminating patch differs how it emits light in each direction and how intense it is in each point. So it's very complex to model the whole one for each point of the location. Therefore, we use simplified models of the light sources. One super simple, basic and constant model is ambient light source that assumes that light is coming from everywhere and it's kind of constant. It doesn't depend on the direction or anything. So we have some like constant light present in this room for all directions. But that can lead to very bad results, and we will see it on the next slide. The second one is just considering single point as emitting light in all directions, and usually light bulbs, instead of modeling all points on the bulb, are simplified down to single point, and it emits in all directions. We can have directional light when the light is coming from just one direction, and we can have spotlight that is just point light limited to some angle instead of emitting in all directions. And earlier in our earlier version, you might see in OpenGL there should have been maximum 8 light sources, but it's deprecated and we don't have that limit anymore. So ambient light is some constant light that is there regardless of other light source. So this can be the amount of light that is present in shadowed areas. So if we use it in combination with other models, it can give us good results. But if we use it separately, we have just flat surfaces because the light is the same for all directions and all points. So we have this kind of flat surface, and the resulting ambient light is the result of surface reflectance and ambient light. We don't consider directionality at all. And it's usually considered white somehow to simulate sunlight-like conditions, and also because we, as we have seen so far, automatically assume white illumination when we're talking about colors. You said apple is red because you assumed white illumination. And all objects appear flat and have the same intensity. Point light is used for modeling bulbs or street lights, and it emits in all directions, while directional light has just like light emitted to a single direction. Any example of a directional light.
The sun.
Yeah, that's the best example. And in the real scenes, for example, here you have light coming only from this direction, for this direction, and you have shadows cast to this side. And spotlight is point light source that does not emit to all directions, but emits to just like some particular angle. And it's used to model, for example, flashlights. So this is a very good example from the real image of the spotlight. Instead of this bulb emitting the light in all directions, you have just like this particular angle. So you spread your light into this angle. And finally, to render, this is called Phong model of reflection. So to identify how much light do we have for a particular object, we have to sum all those parameters. So we have some ambient kind of basis level of the light. We have diffuse reflections. We have specular reflections, and we will see on the next slide what it is. So, and if we have emission, also it's added here. And finally, we get this one. So, for a given shape, we have some basic ambient light that is the same for all points, and we don't see the 3D shape here. We have the diffuse reflection that reflects in all directions. We have specularities that are reflections that are just given very strong for a given direction, and we have no emission in this case. And if you combine all of them, we get this kind of representation that is pretty photorealistic, I would say. So I think this should be easy. Can you guess what kind of reflections do those models depict? So what is this, and this one? Yeah?
Middle one?
Middle one, what is it?
Oh. Okay. No, I thought you meant what the specular highlights in the
Ah,
previous
okay.
image.
Ah, okay.
looks like.
Yeah, so that's right. This is specular highlight. We have incident light, and it's reflected to just some particular directions only. So this is the case for the glossy objects. For instance, like any glossy object. Let's say your box, this one, right? So when you see these highlights, it's because all the lights what is incident from this angle is reflected to a particular fixed angle, and it's not reflected to all dimensions. That creates this kind of specularities, but it's not all from the single point. It's usually spread, considering the angle of incidence. This one. Sorry, this one. So we have the spots that are bright, but other spots that are not bright because for given observation point we don't have reflection in that direction. And if we move this object, can I?
Yes.
Yeah. So if I move this object, then specular highlights are here, but this one is not specular anymore because for this angle we don't have specular reflection, but we have specular reflection for this point and now this angle. So specular observing the specularities depend on the angle. While in contrast to that one, diffuse one reflects in all directions, and like whether you look to this table from there or there, we don't see any specularities, we see the color. And the third one is just like one-to-one reflection. So one ray is reflected into one ray, just one-to-one matching. And what does this give us? Yeah?
Almost a mirror.
Yeah, mirror. Yeah, this one is mirror. And why surface normals are important? So surface normal is the angle that is 90, let's say something. Okay. So we have light coming, we have light reflected, and this one is 90 degrees towards the surface. And we use surface normals to identify, first of all, the intensity, again going back to this one, by the angle between the normal, that is 90 degrees in this 90 degrees, and incidence. So we get the intensity information. So whether we have 90-degree incidence and normal, they match. So we have very bright point. If we have 30%, 30-degree of incidence, so 60-degree between the normal and the incidence angle, that's less bright, and so on. So that's one use of the surface normals, but more importantly, we use them to identify whether we see that point at all or not. So we have a dot product between surface normal and viewing direction, and if that is negative, this means that we have the light coming towards the observer. So like this point, point where the light is reflected from faces towards the observer. So we see that, and whatever points have the normals that give positive dot product with the observation angle are facing outwards, so we can simply back call them. So the idea is that by finding the angle between the between the direction we are looking to the object and between the surface normal, we find out whether this part of the surface is facing towards us or not, and then we control whether we can discard this area or not. And it's used a lot for calculations, also for reflection based on the angle of incidence, the one that I have shown there. And we usually keep normals equal to 1, the length, to simplify the calculations. This is actually the same like what I have already said, like the diffuse reflection is when we reflect in all directions. I have already more or less discussed this one. And in specular reflection, I also mentioned this, that it really matters where we are looking from, because like if we are looking from this point here, we see the specular reflection, but if we are looking from this point and the specular reflection goes there, we don't see it as specular. That's more or less it for, and let me, alright, I will summarize stuff in 3 slides, and then we can continue on the next lecture. Like light, I also have mentioned this one. So emission parameter is used to model the light emitters, and one of the techniques is to put a point light source, make a sphere around that has the emitting parameter and the same color as the light, and it appears as a bulb in the scene. So to summarize it quickly, I started from these 3 things that impact the color, right? We have the illumination, we have the material properties, so whether it reflects this light or absorbs, and if it reflects in what direction and how much. And we have the camera that gets this light and interprets, and we have this Z optical axis to identify what is seen and what is occluded. And finally, we basic idea of this is that for the Phong, according to Phong model, we get the light that is combination of ambient color, diffuse color, and specular color. And in the next lecture we will talk about attenuation and gamma correction. That is more hardware dependent problem. It's not directly considered in the so those two are beyond the foam reflection, but they are used to make the representation more accurate. And yeah, I will start with OpenGL and more how to define those color and what kind of parameters we should use. We can do this next time because it's pretty large lecture and we had to split it into two. But yeah, we will have more OpenGL focused stuff next time. But I think this was more or less a good overview of how it works in graphics to model the appearance and color and light and matter interaction. So any questions so far? Sorry for being a bit over time. Any questions? Is everything clear or nothing clear or something clear and something that is not? So should I assume that you more or less got what I talked about today? Okay.
This is the equation we'll be looking at on tomorrow's
Tomorrow.
lab. We're finally going into 3D, which is exciting.
Yeah, like I don't remember whether I mentioned it explicitly, but yeah, considering the lighting and shadows is like essential for 3D impression, because so far we just had fixed color. For a Pac-Man you have just fixed color, you don't change it by angles, so it's not really realistic 3D. Even if you try to, you can do without this one, you can have some kind of 3D. We have seen that cues when you stuff farther becomes smaller and stuff closer become larger, but for really photorealistic and really adequate 3D, you need to consider lighting and shadows. Your scene to be convincingly 3D. Yeah, if there are no questions, then we can take this up next time and see you on tomorrow's lab.